Whoa! You know Spider-Man, when he flies in the movies, he's back in the MCU, didn't you hear? He cannot fly as cool as some real spiders fly. In fact, real spider flight is even more awesomer than anything you've seen on the silver screen. So let me explain. This has been thought about since all the way back in the time of Charles Darwin, the father of the theory of evolution. So he was actually thinking about how some spiders that he observed could balloon, could release silk, and then apparently be carried off by the wind and float for hundreds and hundreds of miles. So when we look at these spiders, when we observe the spiders that do this, they have two body segments like all arachnids do, or all spiders do rather. And this is a perfect representation of a spider. So when we see a spider doing this, they look like a normal spider, which is, again, this is perfect. And then they have some silk that is emitted from their spinnerets, and it is apparently dragged out by the wind. And then on first appearance, it looks like these spiders are riding on the wind with this silk. If we were being scientists and trying to evaluate this, our first approximation might be that there's some kind of force that's from the wind that is pulling on this string, the silk, which is pulling on the spider, which allows the spider to fly, except this isn't the case. It can't be. Charles Darwin thought about this too. These spiders that fly, some of them are pretty big and too large to be carried by very, very small lift forces like this. Also, it does not appear that the wind itself, when it is blowing, draws out these long strands of silk. So that's another problem. A third problem is that these spiders that do balloon or fly in this way seem to fly most often in very low winds. You'd expect if they were using the wind, they would want stronger winds. So what is going on? Well, fast forward all the way from the 1800s to 2018, just last year, when a team of scientists went back to this question and applied some fun experiments and some physics to it. So what you want to do is isolate variables. If we are doing science stuff here, as we want to do, you want to isolate variables. So what they did is they constructed a box to put these spiders in, like so. And the box was there to eliminate variables. And what variable would we eliminate first? Well, we want to see if wind would have anything to do with this flight. So we put them in a box, obviously three-dimensional, and then we eliminate all the airflow through it, not to say suffocating, but not like any strong wind through it, and yet the spiders inside could still fly. Okay, well, what other variables were still at play inside of this box? A representation of Earth's electric field in its atmosphere. So there's always electricity, small electric fields crackling throughout the Earth's atmosphere, whether you see big flashes of it in the form of lightning or not, it is still always there. And what the scientists found is if you turn off this representation of the electric field inside of these boxes, the ballooning spiders drop. What this says is that without wind, but with an electric field, these spiders can fly. So it does not have anything to do with the actual wind. They just happen to be being carried by the wind. The actual lifting force comes from the electric field in the Earth's atmosphere. This is flight by electrostatic repulsion. And what is going on is that when this silk is emitted from these spider spinnerets, it builds up negative charges along the spider silk. This would be analogous to, say, rubbing a balloon on your head and having your hair stand on end. Some electrons are being taken away and transferred, and there's some difference in charges, which causes attraction and repulsion between like and different charges, and that can lift something if the attraction or repulsion is strong enough. Scientists figured out that this is what's happening. As the spider is emitting the silk, negative charges build up and repel negative charges near the ground and on the spider itself. This is enough to produce the lift that we observe. So why is this better? Because it's not even using air alone. These spiders can emit silk and then glide for hundreds of miles, flying on electricity. And hundreds of miles, Morales? That's got to be cooler for a real spider, and they do. I can feel you shaking your heads at me, but you don't. This is much cooler than anything you've ever seen in the movies, and I want them to incorporate it into the next one. I don't think it's possible. Hello, and welcome to another edition of Because Science Live, the live show on this very channel where I try to take all of your comments, questions, and corrections off the top of my head. Woo! We're live. Anything could happen, and I try to say something interesting, thought-provoking, or insightful about them. Look, I'm not a working scientist. I'm not an expert. I'm just a dude with long hair on the internet that knows a little bit about a lot of sciencey and pop culture-y things. So if you have anything that you would like to ask a big old nerd like me, please put it in the chat where you're watching this, most likely YouTube, and we will get to the best, nerdiest responses. Please do not spam or else we will never select you ever. Isn't that right, Nate?
That is so right.
So right. So what do we got?
The first question is not really a science question, but
it is a science show, so why not?
Chalupa Cabra. Does Kyle spit?
That is a good
That's
username.
Half of why I chose this question is the name.
Fine, please continue.
Does Kyle spitball all the jokes, or do y'all have a ghostwriter?
I write everything in the script. For the main episodes and for these shows and for footnotes, it's either all off the top of my head or improvised, or it's written in the script. I do have producers, people that I work with, that I bounce ideas off of and topics, but when it comes down to the brass tacks of writing stuff, the majority of the gags I write myself, and I have a weird sense of humor, and if it seems that way, it's because it's coming all from up here. Yes. It's being stuck in a emotionless, shapeless volume for years now that's done it to me. I'm unaware of most of what's happening outside.
It makes you go crazy.
A little bit.
Next question is from Tater Salad.
Gotta feed the content monster. Tater Salad?
Yep.
Hey, I saw the Blue Collar Comedy Tour too.
Do you think
you guys remember that?
Yeah.
That was pretty good.
Do you think human beings will need to invest in genetic modification in addition to technological advancement to colonize other bodies in the universe, like bone density or lung capacity, etc.?
Interesting point. Well, that question seems like a real question of what would be harder. Coming up with technology or changing a planet or a spacecraft or a habitat such that it could protect humans enough. Say if you were on Mars, and Mars doesn't have a magnetosphere anymore, so if you're on Mars, obviously you need some kind of pressurized habitat because Mars has a very thin atmosphere. But you'd also need a habitat that could protect you from the radiation that isn't punched away by a magnetic field, a magnetosphere like the Earth has. So you need technology that would do that. Is it easier, or is it more feasible to create, say, a different kind of structure for people inhabiting Mars than it would be to genetically engineer everyone that was going to Mars? I feel like the lead time on the second one is a lot harder, where you'd have to genetically engineer embryos and then wait until they're old enough to go to some place, or I guess they would have to already be born on Mars to quickly see that benefit, or for example. So I think coming up with technology that will help humans colonize the solar system and beyond is probably easier than starting to genetically engineer people for different places over generations. That sounds harder, and you will not have the same ethical problem that you will have. It won't be an ethical conundrum to build, say, a very thick-walled habitat on Mars so you don't get space cancer. That's easy to do. What's harder to do is to convince people who are going to Mars or couples on Mars that, hey, we got to go into your baby's genes and we got to fix them. And also, do you want to pick their eye color while we're at it? It starts to get a little messy. So I would guess that technology in the form of shielding and those kind of things would happen before, or at least we pursue them before we pursue genetic engineering. Although there are things we could change about the human body that would make us more resilient to different forces on different planets. Say reduce gravity. You mentioned bone density, which I think is a good point. Or you could have different genetic sequences that may be able to deal with radiation damage. For example, there is a protein that has a very long name, but it's shortened to DSUP. I believe it's short for damage suppression damage suppression gene, it's live, that we find in tardigrades. And we find that this protein helps prevent and repair damage from X-rays to tardigrade DNA by a significant percentage. So if we could get our DNA through genetic engineering to do something similar to this or produce protein similar to this, we might be more resilient. But again, just building a space house probably going to be easier. What's next?
From JDarg0114.
I feel like I talked a lot for that one. A lot of coffee.
With all the havoc around global warming,
havoc's might not be strong enough of a word.
Which of the many human inventions is having the biggest impact on the rise of global temperature? And would abandoning this be reasonable for modern life?
Oh, well, yeah, I mean, this is the main. So aside from the unfortunate fact that climate change has become politicized, the other way that people push back against doing something about climate change frequently is that it might be economically infeasible, which is what I think you're getting at. And I may have the numbers wrong here, and I don't want to misspeak or misrepresent it, but the largest emitters of greenhouse gases comes from livestock and industry and cars, of course, and those are the main emitters. So you would want to address one of those, or hopefully all of them, a lot to do something significant about climate change. And I think what you're getting at, say, for example, what if we just stopped eating meat? That would put a dent in our emissions for sure, because cow farts, as I will represent here, cow farts are full of methane. And why it's fun, it sounds funny, but clown farts. But cow farts, methane, even though it doesn't seem like there's as many cows as there are cars and they're not emitting as much, methane is a much more powerful greenhouse gas than carbon dioxide, so you don't need as much of it to do the same amount of environmental damage, so to speak, or temperature increase. So one radical solution would be to stop eating meat. Stop producing livestock in the way that we do, raising livestock in the way that we do, and put a dent in our emissions of greenhouse gases. I think that's where people who say, oh, we can't really do anything, stop. And I think that's maybe doing the idea a disservice. We can eat less meat, for example, or we can drive less or adopt electric cars more. We don't have to cancel something completely. Of course, the goal would be to, over a number of years, phase out certain technologies for better ones. But no one is saying we have to adapt to everyone needs to stop eating meat today. Although that would be better, of course, like we were saying, in the long run, the chances of humanity actually banding together and doing that, and for people to all get on board for the same reason, is pretty much zero, right? So there's many different ways you can attack this problem, from changing the way we raise livestock, like we said, to changing the way we drive and we get around and take flights and stuff like that. There's not going to be any one solution. It's going to be multi-pronged, and we have to take it very, very seriously. All of these are going to cost something. It's either going to cost people jobs, or it's going to cost people time, or it's going to cost people things that they like, or products that that we say that you shouldn't use anymore, or something like that. But we're all going to have to make some kind of sacrifice, or at the very least some kind of change to the way that we're doing things, if we're going to have any chance of really fighting climate change. Because just maintaining the status quo and saying something is too expensive doesn't really track with, well, what if the Earth is really uninhabitable for a lot of people? And you logically extend that to mass migrations, national security threats, droughts, famine. I mean, the list goes on and on. So I don't have the answer. No one has the answer. But we need to obviously pick something and hit it hard. That's why I think people become polarized, is that these grand ideas. Everyone, throw your car out the window, get an electric car. Yeah, it sounds radical, and I think that's what polarizes people. So I think that's part of the problem. But we do need to do something radical. Doesn't have to be all at once. I'm rambling. Sorry. Next.
From Space Raptors Infinite.
Oh, geez.
I know.
That's a lot of raptors.
Is there a type of creature with bulletproof armor in real life?
So bulletproof armor is really about having some kind of, well, bulletproofness is having some kind of material that has an ultimate tensile strength where when a bullet comes in and impacts that material, let's say, that the material can withstand the pushing and pulling and stretching forces such that it doesn't break and it doesn't pierce the skin. We have, as humans, found materials that are really good at doing that aren't super thick and that aren't super expensive. We're optimizing these, ultimate tensile strength qualities, like in something like Kevlar. But in the animal kingdom, it's kind of a brute force approach where there are bullet-resistant kind of animals like rhinos, where this isn't really optimized, like metamaterials and dragon skin and all that. It's more about just having really, really thick skin. And that might not pierce all the way into, say, the internal cavities of a rhino. They're more bullet-resistant than, say, we don't have to name other animals that are squishy, but more bullet resistant than other animals. Or, you've heard those stories about, bears being shot basically, in the face or in the forehead and bullets like ricocheting off their skulls. Nature has more of a brute force approach to bulletproofness, but that's because bullets aren't like an evolutionary pressure that the rest of the animal kingdom has had for very long, a few hundred years or whatever. So nothing is naturally bulletproof, but things come close to more bullet resistant, more just as a consequence of the kind of animal that they are. I think we have time for one more question.
From Willie Reimer.
Woo! Willie.
What is the absolute top speed for something in Earth's atmosphere before it burns up?
That really depends on the something. We will get to this exact question in a future episode of Because Science that I may or may not have filmed this morning. But there is, I'm not going to draw a graph, there is something called a stagnation temperature. So when, for things that are moving through the air quickly. So when you move really, really fast through the air, like faster than the speed of sound in air, 343 meters per second, when you're going, 700 or 900 or 1,000 kilometer per second, you start to heat up because air compresses in front of you and it gets hot when you do that and that heat transfers to you. The top speed is going to depend on the robustness of the material that is moving through that and the shape of that material, because when you're going a few Mach numbers, like 2 through 10, let's say, you can get to a stagnation temperature, a temperature at which you're going to reach that temperature and stay there, of many thousands of degrees Celsius, which will ignite basically any material on your person right now and can heat up metal and turn rock into plasma and shatter it apart like happens in meteorites. So the top speed will depend on the shape and the material. So you can have airplanes that are not made to go Mach 2 that can heat up and basically rip themselves apart at Mach 2, where other planes, like experimental planes, can have shapes and heat-resistant materials built into them in such a way that they can go like Mach 5 or something like that. So it really depends on what the thing is made out of. What is the top speed for the most optimal thing that has perfect heat shielding? I don't know. There's a limit on just materials and stuff. I mean, re-entering spacecraft are entering our atmosphere at like Mach 20. So, I mean, if engineers are figuring how fast even a really optimized craft can enter the atmosphere, I'm guessing they've gone through a lot of these calculations. So probably in the Mach 20s is probably about as fast as you can go with something that humans have made and have engineered so far. So that's what I'll say. I'd say look to NASA and their spacecraft. Whew. This was a quick one. I know, we're trying something new here, but I hope you enjoyed this edition of Because Science Live. Spider-Man's back. Wow, cow farts, tardigrade protein, bulletproof animals. We did go through a lot on this show. Thank you so much for joining me for everything on Because Science this week. Next week, we have more of the same. We have another Footnotes, which is very fun. We have another live stream, and we have another main episode that is a little bit out of my comfort zone, I'm going to admit, but it does have stuff in it.
No live next week.
We do not have any live next week because I announced it. There's other things I'm going to announce. But next week, I will be in New York for New York Comic Con, and I will be doing some other stuff. But one of the big things that I'll be doing, if you're in New York City, I will be moderating my friend Adam Savage's panel. We're going to have a nice fireside chat for over an hour while we're in New York, so please come by and see me and Adam talk to each other. If you're there, it's going to be fun. We're going to have a lot of time for questions, and stay tuned for some other stuff that I'll be doing at New York Comic Con, which is awesome. So there's no live next week. Stay tuned for New York Comic Con news and stuff like that. But another main episode, which is, again, a little out of my comfort zone, but we do get into some stuff that will make you go, what does it all mean? So, until that time of that video, be nice to each other, because this is all we got. Whoa! Whoa!